Hello, welcome to another stream. Welcome. Hello, Postcom Sai, Sasalala, Noayo before bed, Out 9, Ivanhoe, the Slayer. The Slayer Riser, and that's how I pronounce your nickname? Yatanasov, Cerimon, Coppercasted, Hodson Blots, Arch Loramis, 7001, Loading BG, hello, welcome. So today is Thursday, if I'm not mistaken, and that means today we're doing Advent of Code 2019 in Haskell. That's what we're doing today, that's right. So in the last week we saw day 10, so today we're gonna continue to day 11 and maybe 12, it depends on how difficult they are. So yeah, about that. You can find the source code of these solutions here. Yeah, let's just get into that. Creating ELF files in Haskell when? I don't know, not necessarily in Haskell, but doing like learning and doing something related to ELF is on my radar for quite some time, so maybe it's gonna be one of the Friday topics, but I'm not sure if it's gonna be in Haskell. To be fair, like if you're asking for an extra challenge, right, if you think the Haskell will give you an extra challenge, I don't think so. Because with the packages like byte string, parsing binary formats is actually relatively easy in Haskell, right? So I don't think Haskell per se is gonna give you that extra challenge on top of ELF. So if that's what you're implying by using Haskell for parsing ELF, probably will be simpler. Yeah, I don't know. Maybe not parser, but anyway, so working with binary formats is not that difficult in Haskell if you use something like byte strings. Alright, so yeah, let's go to Advent of Code 2019. And let's take a look at what we have here. So day 11, I'm talking about parsing, I'm talking about generating valid ELF file that you can link using LD and it will properly execute. Okay, so does it change anything in terms of using Haskell? Does Haskell makes it difficult in for that task? Probably not. I don't think so. Alright, so let's continue. So it's gonna be AoC 2019, and let me fetch the other stuff. Hello, Erhan Kurnas 2000. Welcome. I think I already fetched everything, so let me create the day 11 and just go there, and as usual let me create a file. And inside of that file we're going to create this thing here. So this is going to be the entry point, and let me try to see if it even compiles or not. Is the music too loud? Hopefully it's not too loud. So before we're gonna start reading everything, I think I want to pour a cup of tea. So once we have a cup of tea, we can start reading things. I think I poured everything. Alright, so day 11, right? Day 11. Space Police. On the way to Jupiter, you're pulled over, and there is a link to YouTube. Is that something you can watch on stream? Okay, sure. So, attention, unmarked spacecraft. You're in a violation of space law terms of service. All spacecraft must have clearly visible registration identifier. You have 24 hours to comply or be sent to space jail. It's a horny jail, of course. I'm not clicking on any of this dumb link, okay? So I'm just reading the description. Not waiting to be sent to space jail, you radio back to the elves on Earth for help. Although it takes almost 3 hours for their reply signal to reach you. They send instructions for how to power up the emergency hole painting robot and even provide a small int code program. Okay, so this is one of those problems where we have to utilize our int code interpreter and whatnot. Okay, your puzzle input. That will cause it to paint your ship appropriately. Oh, that's cool. So maybe the inputs or maybe the outputs of the program needs to be hooked up into some sort of a canvas, right? And then you will have to paint on that canvas, and then you will have to display it and see what's written there. That's actually pretty interesting. I really like that. So there's just one problem: you don't have an emergency hull painting robot. You will need to build a new emergency hull painting robot. The robot needs to be able to move around on a grid over a square panel on the side of your ship, detect the color of its current panel and paint in the... Okay, so you also have to hook up inputs and outputs of that program to something. So the inputs is going to be sensors, and the outputs is going to be probably actions like step up or down, left, right, paint something, or well, at least this is how I imagine it. The robot needs to be moved to be able to move around on the grid of square panels on the side of your ship, detect the color of its current panel and paint its current panel black or white. All of the panels are currently black. Alright. The int code program will serve as the brain of the robot. Okay, I guessed correctly. The program uses input instructions to access the robot's camera. Provide 0 if the robot is over a black panel, or 1 if the robot is over the white panel. Then the robot will output two values. First, it will output a value indicating the color to paint. So this is literally the Turing machine, the Turing machine I developed in GP. Remember how I did that, right? So essentially I did the genetic programming on so a bunch of small robots that were programmed with state machines, like similar to Turing ones. It's literally that, but in form of an int code program. That's very interesting. Alright, provide, then the program will output value. First, it will output the value indicating the color to paint the panel. 0 means to paint black, 1 means to paint white. Second, it will output a value indicating the direction the robot should turn. 0, it should turn left 90 degrees, 1 means it should turn 90 degrees. After the robot turns, it should always move forward exactly one panel. Yeah, it's literally a Turing machine. Like two-dimensional one, actually. The robot starts facing up. Alright, the robot will continue running for a while like this and halt when it is finished drawing. Do not restart the int code per computer inside the robot during this process. For example, suppose the robot is about to start running, drawing black panels as dot, white panels as hash, and the robot pointing the direction it is facing. Okay. The initial state in the region near the robot like this. The panel under the robot, not visible here because, okay, it's drawn, it's also black. So any input instruction to this robot should be provided 0. Suppose the robot eventually outputs 1, paint white, and then turns left. Okay, I kind of understand what has to be done here, so yeah. So this is just an example. Before you deploy the robot, you should probably have an estimate of the area it will cover. Especially you need to know the number of panels it painted at least once, regardless of color. In the example above, the robot painted 6 panels at least once. It painted a started panel twice, but the panel is still only counted once. It's also never painted the panel it ended on. Build a new emergency hull painting robot and run the encode program. How many panels does it paint at least once? Okay, so it doesn't need to be outputted. So somebody asked, what's your guess on part 2? I guess on part 2 is to actually display what it painted, and maybe it paints number of some sort of a number or some sort of a code, and then you'll have to actually put it there. It'd be cool if you also rendered on SDL so you could see the image it's generating. So you can, I don't think it needs to be done with SDL, like you can do that with text, right? So yeah, and I think this is going to be the part 2. I think the part 2 will be about actually, you know, so maybe the input actually encodes a message, right? It encodes a message, you have to draw the message, and you'll have to display it. But text is boring, yeah, but doing something with GL may take more time than it's needed. Alright, so let's get let's get started. Get your puzzle input. It's not that big actually, it's actually a pretty small puzzle input. Alright, so input txt, there we go. Cool. So we also want to import int code implementation, right? So I guess the easiest implementation here, so like amount of panels it painted at least once. So, but if it's overlapping, right, if it's overlapping and stuff like that. Do I want to keep track of all of that? I think I do want to keep track of all of that, right? So I'm just going to put these values in a hash table, right? So I'm just going to, yeah, I'm going to maintain maybe a set of white tiles, right? So and essentially I'm going to also maintain the position of the robot, and knowing the position and the set of white tiles, I can easily tell the robot what's the tile and whatnot. Alright. Okay. So let me actually restart everything. It's not going to restart properly because I also have to do something like this, because int code implementation is located one level above in the directory hierarchy, because it's shared between several solutions simultaneously. So this is basically what we're trying to achieve here. I want my implementation to be actually usable for all of the solutions that involve int code for some reason. I don't know why I want to do that. Let's introduce the state of the robot, right? So I'm not sure if it's going to be the state of the robot. But it's generally going to be the state, right? So it's some sort of a state, and the state includes a robot position, which is going to be just this, like this, and white panels, right? So and the white panels is going to be simply a set, right? A set of these vector 2s, and I think we already used this approach where we defined our own vector 2 type, so I think I'm gonna do that one more time because this type was extremely convenient. Maybe I should also share it between several solutions because it looks like a very useful type. So let's see, it's gonna be vector 2, and it doesn't have to be like that, by the way, right? So, and also we need to import qualified data set as S, and there we go, we'll be able to do this kind of stuff. Might as well also do deriving show and whatnot. So this is our state. So we can also have initial state, which is yeah, so the initial position of the robot doesn't matter because all of the actions that it performs, they are relative. So we can assume that initial state is going to be like the initial position of the robot is going to be just, 0, 0, or something like that. Robot position. Position is too long to type, so I'm going to actually call it pose. And it's going to be just vector 0, 0. Like that. Next thing, amount of white panels is going to be just an empty set. And I forgot a very important thing, by the way, chat. I forgot to introduce the direction. So we're going to have a dir, and initially it points up, then we're going to go clockwise, I suppose. Right, down, and left. And of course, it's going to be deriving show. So you see, not only Ada encourages you to create shit ton of different types, right? Haskell also encourages you to do so. So yeah, and we can have a robot direction, and it's going to be just a direction. There we go. So we have a position, we're going to have a direction, a robot tier, and it's going to be equal to up because that's the initial position. And there we go. Here is the initial state. Initial state of our thing. Cool. So what I'm thinking is, we need to have some sort of a function that maybe accepts the current state, right? It also should accept the machine. Machine, and should probably return next state a new machine. To be fair, if I need a function that accepts the state and the machine and returns new state and new machine, probably the machine is part of this state. If you think about it, right? So probably it is a part of this state. So let's actually call it a robot brain, and it's gonna be a machine like that. So so we can maybe rename this entire thing to something like make state, and it's gonna accept the machine, right? And it's gonna put that machine into the state, and after that it's gonna be something like a robot brain, right? Robot brain, and gonna equal to the machine. There we go. So, and because of that, this kind of thing is gonna be just the next state, right? All right. So next state. Let me see. So do we really want to do the next state? I don't know, but basically what we want to do here, we want to repeat the process until the machine halts, right? Until the machine halts. So how does it work? You will need to build. The program uses input instruction to access the provide 0 if the robot is over a black panel, 1 if over. Then the program will output two values. First, it will output a value indicating the color to paint the panel the robot is over. 0 means the paint. Okay. So I'm just thinking what's going to be the best way to do that. Turn left, turn right. So we have an absolute direction here, right? So maybe we'll also introduce something like turn, right? And we can have something like turn left and turn right, right? I think that's gonna be interesting. Deriving show, right? So, and then I want to have a function that takes a turn and also a direction and returns a new direction depending on the turn, right? So essentially, if you have a turn left, right, and your direction is up, you have to repeat that like 4 times. Is that even a good approach? I don't know. Could be. I think it's extremely dumb, but maybe it is what it is. Right, turn right, down, left. And both, what's up? Hello. So yeah, we're programming in Haskell, your favorite language of all time, by the way. Down, left. So what I'm thinking is, I think I'm a big dummy. I think direction should be from 0 to 1, right? And when you add a value, you're rotating clockwise. If when you subtract value, you rotating counterclockwise. Have you considered? Well, it's almost like I was about to explain, like. Holy shit. It's almost like I was about to came to the conclusion that we need an enum here. Why did I read the chat? Think I should stop reading the chat. Holy shit. Anyways. So as far as I know, speaking of enumeration, right? We don't really even need to worry about this kind of stuff. So you can literally just do it like that, and it's gonna be just an enum, right? So, and I think enums are automatically derivable. Deriving show. Alright, so, and I even need to do anything. So, because essentially if I do suck for the up, right, it automatically goes to the right. So success for the up is going to be right, down left, and the previous, for example, priv, right, is going to be up. But is it a priv? Let me take a look at the enum thingy. It's a pred, sure. It's a predecessor. And there is a problem because right collides with the right from prelude, right? Right collides from the right from prelude, so we'll probably have to do something like this. Alright, those, have you considered renaming your name so it doesn't collide with everything? I'm helping. Sorry. So here is up. So it's gonna be. So is there something like info? So there should be probably something like minimum, right? Enum from. I guess there's no way to get the minimal one, so okay. What's interesting is that it does not rotate around, right? So it does not rotate around if you do something like this. Yeah, you have to also do it like that. It's not gonna go around. So enumeration does not rotate, right? Enumerations do not rotate, and it's not particularly a great idea. So essentially, you will still have to always convert it to an integer, right? Like from enum. Right. And what's interesting is that the modular, right, the modular doesn't really work correctly. Or does it? Okay, it does work correctly. This is perfect. So that means to turn left or turn right, you still have to convert between integers and whatnot. Which is okay, I suppose. So we can have turn left, where you have a direction, and it returns you a new direction, right? But this one, add, is going to be turn right, I think. Yeah, it's going to be just right. And what is it? From enum, dear, right? Then you do +1, then you do a modular. And how can I know the size of this entire thing? It's kind of strange, like, you can do a lot with enumeration, but how can you count the amount of enumerations? I don't think there is an easy way to do that, unless... what is enum from? Enum from you, and yeah, and if you start from here, it just continues. So the only way for you to know the n, right, is to do something like n enum from you, maybe even enum. Yeah, something like 2 enum 0, 2 enum 0, and then you take the length of this entire stuff. Holy shit, it's so dumb. Okay. 2 enum, so you take 0, but you have to also indicate that it's a direction, right? So after that, you do enum from to generate all of the enumerations, and then you take a length of it. And this is how you can know how many values in enumeration you have. Nice language, thank you very much. So now, if I try to do this thing, it's gonna be something like this, and yes, yes. So can I even do something like that? Will it work? All right. So what do we have here? Oh yeah. So after that, what you have to do 2 in num, right? So convert it back. And is it gonna work now? It's gonna be something like 19. Could not match expected type. Actual type is dir. From a num integer +1 mod. Okay, so this is basically what it's going. So that means I'll have to put it like this. Oh my god. Okay, so finally it works. Now, if you have turn right and you have u, it go to the right. But if you have turn left, by the way, and yeah, for turn left we have to actually create it like this. Right, it's going to be turn left. We might as well actually have something like turn right, and we can accept integer here. And what does 0 mean? 0 means that turn left 90 degrees, so that means it has to be minus. And if you repeat that here as 1, it's going to be plus, right? Right, and so you can actually use this thing like this. Cool. I don't really like this approach. So, but we can, yeah. We can kind of go back to this idea of turn, right? And have it like turn, hello Ronak, welcome to the stream. Turn right, and it's going to be deriving show enumeration. Show enumeration, and since 0 is a turn left, right, since 0 is a turn left, this is going to be like that, and this is going to be turn right. So it's pretty much the same, except instead of integer here, we have enumeration. So now maybe I'm gonna call it like delta or something, right? And then I'm gonna do case delta of turn left is gonna be this, otherwise turn right is gonna be this, which is like literally the same thing, but like this. And let's just remove this entire stuff. Cool. Is there any more way to simplify that? Maybe. So we can also do things like that. And I lost n apparently. Let's do where. I have to do it one more time. To enumeration 0. Direction. Enum from. And length. Cool. Is it gonna work now? So what does it want from me? Turn. Okay, so that's basically the idea. That took too much time to implement. Wasn't worth it at all. But now it's type safe. So another thing, we can also try to do something like 2 enum 0 here. Oh, by the way, if you have an enumeration, does it automatically create the monoid? That would be actually pretty cool if it out. Well, I mean, the first element of enumeration is not necessarily monoid, so I don't think it's worth it. All right. Okay, so this is how we can do all of that. Next state. So for the next state, we just need to add a current thing to the robot, the current panel, right? So a panel. So what we do here? White panels state, white panel state. And what I want to do, I want to check if you know, the current position is contained within the white panels, right? If it is contained within the white panels. If it is, that means the current panel is 0. If it's not, it's actually black. But I don't quite remember, right? I don't quite remember. So let's actually go to Google and dataset. What's going on in the chat? Do we need to ban anyone? I don't really follow the chat. Is everything okay, everybody? If somebody needs to be banned, just let me know. Dataset. No need to ban, just people being. Oh, okay, that's normal. I mean, so that's totally normal. Okay, so something like contains ban for weirdness. Member? Is there something like member? I think there should be. Yeah. So essentially, you can take an element, and it can check if it's a member of it or not. Okay. So as member, so we can take the element, which is the position of the robot, right? So I'm gonna call it pose. And white panels. And if this thing is located here, so should be okay. So then it means it is going to be 1, otherwise it's going to be 0. So this is how we know the current panel. So maybe I should destructurize everything because it's not particularly convenient. So something we can do is probably state. But I also need to keep track of the state, right? So I also need to keep track of it. So it's going to be state, robot pose is going to be position, robot direction, and robot brain, right? So this is going to be the brain, and white panels is WS, right? So it's going to be WS. And the easiest way to check that is going to be WS like this. Okay. So in int code we had something like push input, right? And you can push a value into the machine, so it will push it into the input. And that's exactly what we want to do here. We want to push input panel into the brain, right? We're pushing this thing into the brain, and I guess the next thing we want to do, we want to wait for a value, right? We're waiting for a value, which is very interesting. So we can do something like this. It will output indicating the color to paint. Okay, so that means we're gonna have a color and wait for output like this, and it's gonna be so then it creates a new brain right here. So right, it creates a new brain. Cool. So after that, we need to wait for another value. Brain turn, right? So because of that, I'll probably have to rename this function. apply turn. So let's actually call it like this. So it's going to be called apply turn. Wait for output, brain, like this. So you see, we push a value there, and we apply the output, and now we have a caller, and now we have a brain. We have a turn, right? So because of that, a pair machine maybe value could be a monad. So, and instead of let ins, I could have been actually using do notation, but I think it's too much time for me to figure out how to make it a monad. Alrighty, so now I need to do the thing. So now I need to apply all of this stuff. Alright, but to apply all of this stuff, I'll have to do this thing like this. So first we are rotating, right? So first we are rotating, and then we make a step, right? So that means the robot deer is basically apply turn to enumeration turn, and then we apply that to a direction, and this is the new direction. So interestingly enough, a new position is basically this new direction, but step towards, or maybe let's call it step 2, right? You take this new direction and you take the previous position and you step towards that new direction. So a new robot brain is essentially going to be the brain prime after these two steps. And after that we need to update white panels. Okay, so depending on what's the color, whether the color is a black or white, we need to remove or add a thing there, right? So so let me see if we can also do something like color. We might as well actually introduce the notion of a color then, right? So since we have types like vector2, direction, turn, we might as well also introduce something like color, right? And we can call it black and white, right? And the order will naturally make this 0 and 1. Right, it will naturally make it 0 and 1, and let's make it an enumeration. I feel like I'm programming an Ada, to be fair. Like, I literally feel like I'm programming an Ada. Because this is exactly what you're supposed to be doing in Ada. You have to create, like as many tabs as possible. But maybe it's not that particular Ada thing, but I don't know. Alrighty. So this is that, and then I can do what? Case to enum of black, and then you can have another one. Undefined white. So there we go. So this is the new stuff. You know what? I might as well actually like do something like this. Dear prime, and just indicate the new direction and just use this new direction everywhere, so it's a little bit more readable. Hopefully it is more readable. Our Ada, yeah. Alright, so here's this thing. If it's black, right, we need to remove that position from the white panels, right? Since I'm using like let already, I might as well put this thing here. I think it would make sense to put it there. Alright. So let me put it like that. Okay, so Yeah, it has to be undefined or something. There we go. Cool. So black. So how do you remove things? How do you remove things? Remove or delete? Is it delete? Okay. I wonder if what if we try to delete something that does not exist in a set? This is something I never thought about. Let me see. So if I have an empty set, right? S delete. I'm gonna try to delete 69 from an empty set, and it's okay. So this does not generate an error. This is actually perfect. This is exactly what I want because I can now do S delete the current position from the white panels, and now if I painting it white, I'm just inserting them. Perfect. This actually works out really fucking perfect. As insert position into white spaces, and that's it. That should be it actually. This gives us like a single iteration. This gives us a single iteration, except for this kind of stuff when this thing may return nothing, right? So if the machine halts, you constantly have to check if the machine is halted, so which is not particularly great, but I mean that's what we have to do. Okay. Looks good. Is it gonna compile? Is it gonna compile? Let's find out. And it's not gonna compile because we don't have a function step 2. So it accepts the direction and the position and creates a new position towards that direction. Nothing special. Nothing particularly special. I'm just thinking. Yeah, maybe because of that I want to rename this function from apply turn to turn to as well. So we can turn to and then you can step to. So that's pretty cool. Okay, step 2. So, and in here we take a direction and a position, and then it creates a new position here. So, depending on direction, right, so we're gonna have it like this, left, right, down, and in here, let me see how we can do all of that. So this one is X and Y, right, so we're gonna use it like that, and if it's up, I think we're gonna approach it like this. I'm not particularly sure if I like this approach, but maybe it's gonna be like this. Okay, so up, right, so I'm gonna assume that Y goes down, right, so because it kind of makes sense. So that means if you go up, you subtract Y. If you go left, you subtract X, right, like this. If you go right, you add X. If you go down, you add Y. There we go. So this is what we're doing. So this is the step 2. That makes sense. Is it gonna compile now? Okay, we don't have. For example, for some reason, it's not particularly happy with color. Black and white. Okay, so this has to be like this. Alright. So maybe to enum. What I'm trying to do here, I'm trying to convert an integer to a color, but for some reason it doesn't really work. Oh, because the value is an integer. Okay. Okay, so it's Haskell being Haskell yet again. So from integral, right? So I think this is what I have to do. And this is a very similar situation you have to do from integral here as well. Okay, so, and this thing has to be ordered. So, essentially, in Haskell, you have to explicitly convert between different types of integers, which is actually a good idea, I think, generally, because, I mean, yeah. I think Jaya also forces you to do that, and like Ada, I think Ada also forces you to do that, because in Ada, different types of integers are literally different types, so you cannot just easily convert between them, like automatically, and it does make sense. Okay, or RD. So this is basically the interfaces we have to implement, and now it compiles. There we go. So we have our domain-specific vocabulary. We have a position, we have a direction, we have a turn, we have a color, and all of these things are types. Everything is type safe. Everything is super safe. Can your Rust do that, by the way? Excuse me? How do you get your desktop share to not occupy the full screen area, yet it does not appear to have skewed proportions? What are you guys talking about? I'm using i3. This is a tiling window manager. So I can actually just put something here, like... you probably cannot see that, but I can add additional thing here. So it's just a tiling window manager. That's what it is. Make sense? And then I have a camera on top of the everything else. At any point I can just close the chat and say fuck chat, and there is no chat anymore. And then I can open it again, of course. Not gonna do that. Just joking. Alrighty. So, okay, so, but this is only one step, right? It's only a one step. So we need to keep doing that until the brain halted. Is brain halt? Boolean, right? So and essentially what you do here is robot brain and is halt. So that's the whole thing that you need to do. Might as well inline it, but I don't know. So whatever. So and essentially once you get the state, you want to iterate this state with next state, and you want to drop while brain halt. Yes. Drop while is brain halt. Can I do drop until? Is there such thing as drop until is brain halt? So, but I mean, if there's no, I wonder. Like, I personally am not a big fan of until logic, but I think I'm starting to appreciate it because sometimes that's exactly what you want to do. So, is there drop until? Not in the standard library though. Brain power when? Soon. Don't worry about that. All right. So, but we have to actually solve the problem, right? Building your emergency hull. How many panels does it paint at least once? Okay. So we also need to introduce the following thing: white panels, touched panels. Right, and it's also empty. So what this thing does, right? So this one keeps track of the white panels. This one keeps track of the touched panels at all, and the result is essentially how like the amount of touched panels. And the way we're gonna do that, so touched panels is TS, and the new touched panels is always as insert position into TS, so we always keep track of them. If in white panels we can remove them sometimes, right? The touched panels is actually, you know, all of them, everything that we touched. And I think in here, excuse me, what are you not in the scope? Ah, this is because I actually never did it here. Touched panels. So is it going to do the trick? Hopefully it's doing the trick. Cool. So now we need to do a part 1, I suppose. Part 1 is going to accept the machine and then it will return the result. Right, so here's our machine. Then we need to construct the state. Right, so what we do here, we make the state from the machine, and then I'm iterating the state with the next state here, and I'm dropping while, not is brain halt, right? So after that, so it basically it keeps applying next state on the state, and after that I take a head of this entire stuff, right? I take a head of this entire stuff, and I just take detached panels, and I take the size of them. I think it has to be something like S length, and yeah, essentially it will give me how many of these panels we touched, pretty much. Yeah. Make a state, iterate through the state until the brain has halted, and then just extract the amount of panels that we touched. Pretty straightforward, nothing special. Cool. Is it compiled? Does it compile? No, it does not compile, probably because there is no such thing as S length, but maybe there's something else like S size. So let's find out. And yes, there is such thing. Cool. Now I need to... Yeah, in int code I have something like machine from... Yeah, machine from file. You can load the machine from file. Oh yeah, bounded. I forgot about bounded. That's a good point. Bounded. Maybe I can. Yeah, that's cool. Let me try it. Let me try. Didn't think of that. Wait, I'm looking at the wrong thing. Bounded. Okay, I can, thank you. But I'm too lazy to do that, because that means I'll have to go and bike shed this entire code one more time, and I just don't care. Seriously, come on. So, like, this is not even the most interesting part of the problem. This is the most interesting part of the problem, and there's literally zero comments on this part, because it's, I mean, yeah, you need to understand it to actually have any comments on that, right? Literally bike shedding. Anyway, so whatever. It's easy to argue about the color of the bike. Shit. Let's argue about something more important. Okay, so read file, and I think I want to have some sort of a samples, right? So is there any samples that we can use, or like at least something that we can test? I don't know. I guess there's only input. Okay. There's also a great chance that my program is gonna fail because of some of these assumptions may break really easily. But yeah, anyway. So let's read the input. We read the file, and maybe I can do something like machine from file. Right? It's a machine from file, and I'm just gonna do input txt. You're saying the chat doesn't understand your code. I'm gonna tell you something, you're goddamn right. You got me. So I loaded the machine. Isn't that cool? Anyway, so then, once I loaded the machine from a file, I'm gonna apply a part 1 on the machine, hoping that it's gonna give me the result. It's doing things. I don't know how. Okay, non-exhaustive pattern matching. Brain just color. Okay, it's epic. It did the thing. Isn't that amazing? I think it's goddamn amazing. So brain just color. It feels like it tried. It tried to do the thing with already halted brain, right? So why do we have a halted brain in here? Why do we have a halted brain? That's a good question. So maybe we should put some sort of prevention. Right, if the brain is halted, right, if the brain is halted, simply do nothing and return the current state. So that sounds like a reasonable solution, maybe. I don't know. So let's put it like this. Can I... Emacs, please stop. Is brain halt? Okay, actually is halt brain, right? And if it's halt, I just return the state. Otherwise, we're gonna put it like this. Okay, and it works. There we go. So essentially, it's just, you know, not gonna do anything with the state if the brain has halted. Right, once it has halted, like there's nothing to do. So let's just ignore that particular situation. So that kind of makes sense, I think. I think this kind of makes sense. Okay, let's give it a try. And non-exhaustive steal. Okay, so it's really strange. Come on. Alright, so let's make a cup of tea. So that means the brain was not halted. Right, the brain was not halted. But we provided the current panel. And it halted afterwards. It only halted afterwards. So that means, yeah, it can halt like at any of these points, which is... yes, that's basically the thing I want to say. So it literally can... And it's kind of... Yeah, and I need to handle it somehow. So here I will have to handle it somehow, but I need to think how to do that. Again, it would be kind of cool if the pair machine, result of the machine, was some sort of a monad. But I don't know. So essentially, if something like this happens, so brain is not halted yet, but providing the current thing. Is there any information on how this thing halts? After robot turns, it should always move forward exactly one panel. The robot will continue running for a while like this and halt when it's finished drawing. Do not restart the int computer inside the robot during the process. Okay, I won't do that. So we can actually take a look at how many of the states it generated. Right, so we can take how many it's generated, so we can return a list of the states. We can take them while, right, we can take them while the brain is not halted, right. Okay, one more time. And if... Okay. Okay, I'm gonna actually map it with robot pose. Okay, so these are the positions, right? These are the positions. That's a lot of fucking positions. Holy shit. Okay, and then it stops. So these are all of the different positions the robot been in. And then it catches the fire. Holy shit, that's actually... yeah, I'm sorry for the bitrate. I'm really sorry for the bitrate, but that's a lot of positions. I didn't expect that. I didn't expect this amount of positions. Alright. So, yeah. I think so far there's nothing particularly suspicious. There's nothing particularly suspicious. It's just the brain can be not halted. So the brain might have some things to do before actually halting, right? It might have some things to do before actually halting. So, is there any way for us to just, you know, flash the rest of the execution before, you know, waiting for the input or anything like that? That would be actually kind of cool, because that would simplify my life a little bit. So, you can wait for the input. Machine from memory. Yeah, so this is a cool idea. So we have a write, I think read. Yeah, here's the read. So essentially, yeah. If you have nothing in a read queue, our machine crashes instantly. It would be kind of cool to have a function that instead of crashing, it will return you back. It will return you back if your input queue is empty. So essentially, something similar to wait for input, wait for the output, I mean. Wait for output, yeah. But for the input, essentially execute until program requires input, and once it requires input, it returns the execution back to you, so you can push the input there. So that would be kind of cool, and that would simplify a lot of things. But I'm not sure how to implement that. So implementing that is just like stepping the machine, but during the step of the machine, if your input is empty, it's gonna instantly crash. So you also have to modify the step of the machine. Right, and in the step of the machine, yeah, you have this kind of thing. Well, you can always, within the step of the machine, you can always check the current instruction, right? You can always check the current instruction and see that it's a read, and then you can assert that you have an input. I think it should be possible to do something like that. Anyway, before I'm going to implement that, yeah, I want to make a cup of tea. So wait for output. And we can implement something like wait for input, right? Wait for input. Wait for input. You accept the machine, right? And it should return you a new machine always, right? If the machine is halted, it will just return you a halted machine. Nothing particularly special, right? So this is what I want to have here. Wait for input. So you can wait for output, and you can also wait for input. All right, so let's make a cup of tea. And do you guys have any questions while I'm making a cup of tea? Anything you want me to ask? Just making a cup of tea. Nothing special. Can you explain state modes in Haskell? Yes, I could, but I feel like I would be wasting a content for my YouTube channel. So, and I don't like wasting the content for my YouTube channel for free, if you know what I mean. Maybe eventually I will make a video about that. Oh, what's up, Hamiko? Welcome to the stream. Alright, so I'm gonna go turn on the kettle, boil up some water, and I'm gonna be back, and we're gonna continue solving this problem. It will be definitely easier to solve all of that in something stateful, but in Haskell it's also okay, I guess, if you have like right functions and whatnot. Alright, so don't go anywhere. I'm gonna be back soon. Hello. Welcome. Does anyone know any resources for using effects library in Haskell instead of Mon and T? I don't know what is effects library, but in a majority of situations when I want to like learn how to use a particular Haskell library, I just read its source code, and it's usually like enough, because the signatures in Haskell basically explain you how the pieces fit together. So you can try that, right? I rarely read like anything on how to use libraries in Haskell. I just straight up read their source code, or at least their you know, generated docs, like basically their interface. It's usually very self-descriptive. Okay. Cool, but I'm still a noob and can understand properly stuff. Well, in that case, you need to fix that first before using any libraries. Like, isn't that obvious, right? So if you can't read basic stuff, like, learn how to do that, and then go back and learn the libraries that use that basic stuff. All right. So let's continue. So I need some sort of a function that accepts the machine and tells us if the current opcode is step. That's what I want to know. Is not really step, is about to read, right? And it's going to return a boolean, right? So essentially what it's going to do is going to take the current opcode, you know, decode it, and see if it's a step instruction. And if it's a step instruction, it's going to return true. And we're going to use this predicate to check whether a read is about to happen. And if the read is about to happen, we're going to check the input. And if the input is empty, we're going to stop the execution and let the user provide the input before crashing, right? Because right now, if you're trying to read, if the program trying to read and you have nothing in the input, it's going to fail miserably, and we don't want that to happen. All right, so I'm going to go to the kitchen and just, you know, pour myself some hot water for the team, and I'm going to be back. Okay, is about to read. Let's see. We need to extract the opcode. We need to extract the opcode. So this is pretty straightforward. The only thing you need to have here is the IP and the memory. So here we have that IP and the memory. Then we have the opcode, and we need to decode it. So we at least need this kind of stuff. Do we need the base? We need the base only for some other bullshit, so I'm not gonna do it here. So this is the base, this is the opcode, this is the this stuff, and yeah, opcode equal read, read, and if it's equal 3, we are about to read. So this is essentially how we do that, right? So we take a look at the machine. If it's if the current opcode is a read, this is going to return true. So we might as well also ignore this entire stuff because we don't need the modes of these things. All right, so wait for the input. Okay, so so iterate step machine, right? So here's the machine, and we're dropping while. Here's the machine. The machine is not halted. The machine is not halted, and not is about to read. Not is about to read and get input for the machine. So it's actually m, and get input n is null. Right, so this is the condition. It's about to read. Yeah, so it's both of them. About to read and the input is null. And yeah, it's not cool. Afterwards, we just take the head of this entire thing, and I guess that is it. I guess that is it. So we have a thing that waits for the input. All right, it just waits for the input. All right, let's see if it's gonna compile or not. So it didn't work because I forgot to put this thing here. All right, so I might as well actually extract this to some sort of a separate function. Yeah, I don't know how to. Okay, stop for input. This is how I'm gonna call it, and then I'm gonna put where stop for input, like this, and it's gonna be /m stop for input. There we go. Right, drop a while stop for input. Is time to stop. Drop while. Okay, so yeah, that's kind of interesting. So it has to be like a reversed logic. Time to stop is when it is halted, or when it is about to read and the input is null. That's when it is time to stop. So you drop while it is not time to stop, right? So that's basically wait for input. Right, so you iterate the machine and drop the states of the machines while it is not time to stop, and the time to stop is when the machine is halted or when the machine is about to read something but there is nothing to read. So this function will let you stop the execution before it will crash because there is nothing to read, so you can provide an input or something. Make sense? Hopefully that makes sense, and if I try to rebuild that, everything rebuilds successfully. Alright. It's been a while since you shaved your head. So, yes. So, what you mean? You're saying, like, my hair should about to grow back or something? Well, I shave it regularly. So... I think adding to today would be useful. Okay, probably. Update CMD project. Sure. Still on day 1, by the way, still on part 1, unironically, day 11. Alright, so I'm gonna put it here. There we go. So here we go. Okay, so how we're gonna do all of that? The way it is going to work, we push an input and we wait for the... wait for input. Right, so essentially, after executing everything, we want to flush, like literally everything, before saving it as a current brain. So on the, it will be halted if there is some additional execution to finish, right? And also, when you're creating the machine, we also want to prime it and wait for input. Right, so we're gonna just, you know, execute it a little bit before it will ask for input. And yeah, this will make sure that on the next time, when the execution is finished, this condition will actually, you know, work properly. Hopefully, we'll see. Let me see if it's gonna work. Okay, everything seems to be compiling, and we are about to do this thing. And parse region, okay, it didn't work apparently. Parse region? This is not what I wanted to do. I wanted to, okay, machine from file, this is what I wanted. And maybe I want to change this back. I want to change this back to just integer. Right, so I actually drop while this entire thing is not halted, right? I drop while this entire thing is not halted. Then I take the touched panels and I just take the size of the set of the touched panels. So, and that way, I forgot to take the head of it, of course. I forgot to take the head of it. And alright, so we are about to do this thingy. Is it gonna crash? It didn't crash. 2392. What do you guys think? Would this be a first try? Well, at least my hypothesis of this thing being like having unfinished computations is sort of correct, right? Once I implemented wait for the input, it solved all the problems, but now we have 2392. And I'm about to put that thing in here, and since I'm not a God coder anymore, probably it's not gonna be a first try. 2392, so let's submit that, and it was correct. God coder restored. Oh shit! Ah, fuck. You were too late. You were too late. No, I overshot the bet. So yeah, okay, so that was cool. I guess I have some God coder powers in me still left. Who would have thought? Who would have thought? So yep, and I implemented a very useful function. Okay, so okay, well, the next time I'm gonna do the bets, right? Or the next time I'm gonna do the bets. Continue to the part 2. All right, you're not sure what's it's trying to paint, but it's definitely not a registration identifier. Fuck. Imagine if I try to render this thing and it's gonna be something MongoDB and I'm gonna be banned for that. That would be the most the funniest ban in Twitch history. Alright, so it's not a registration number. The space police are getting impatient. Yeah, drawing dicks, exactly. Checking your external ship cameras again, you noticed a white panel marked emergency hull painting robot starting panel. The rest of the panels are still black, but it looks like the robot was expecting to start on a white panel, not a black one. Okay. Drawing horses, yes. Based on the space law space brochure, at the space police attached to one of your windows, a valid registration identifier is always 8 capital letters. After starting the robot on a single white panel instead, what registration identifier does it paint on your hull? Alright, we're about to find out. We're about to find out. Alright. So, let's pour a cup of tea. This one is gonna be kind of tricky, because we keep track of them through a set, and by painting white to black, we basically remove it from the list of whites. So that means we have to invert the logic completely. Invert the logic, but maybe we can introduce like another set here. So black panels, why not? Like a black panels, it's like an opposite. So we can keep track of them simultaneously, right? Can keep track of them simultaneously. So this one is gonna be black panels like this, and the new ones is gonna be like this: case to enum from integral color. if it's a black, we insert the position into the list of black things, and if it's a white, we are deleting it from the position of the black thing. So we basically keep track of whites and blacks simultaneously. So we do these things simultaneously, I think. Yeah, it's pretty cool. So probably it will make the execution even slower, but we're about to find out how slower it will become. So where is the initial thing? We have a raid from Curtis Sheeran. Thank you so much for the raid, and welcome. We're programming in Haskell. Do you guys program in Haskell? Okay, and everything seems to be cool. Everything seems to be cool. Now, I want to see if it doesn't slow down the execution too much. So it shouldn't actually. It doesn't. Programming in Angular. Interesting. Isn't that like a framework that lost to React? If you know what I mean. Anyway. Afterwards, we wanna render this entire thing. How are we gonna render this entire thing? That's a good question. So we can actually figure out the boundaries of the black panels, right? So to do that, we can try to find the minimum, right? So once we found the boundaries, we can iterate through these boundaries, right? We can iterate through these boundaries and basically check each thing being in a list of blacks or not. And if it's in a list of blacks, we find it one way and then another way. Makes sense. Relaxing in Angular, can only choose one. Okay. Lost to Angular, but there is still way more Angular code to maintain out there. Well, kind of being deemed as a technology for legacy projects and not for new hyped startups is kind of like a losing situation for me. It's like Java. Imagine being compared to Java. That doesn't sound like a win to me. Sorry. Yikes. There's also a lot of Java code in maintenance, but Java? No, sorry. Alright, yeah, so we need to figure out the boundaries. I'm coding in Java, right? I'm really sorry. I used to be a Java developer as well. I mean, like, I've been in the Java enterprise environment for very long. I'm sorry, nothing. Everything's okay. Java is cool. I love Java. I programmed in Java for many years. Everything's okay. You didn't hear anything. Java is cool. It's the best language for JVM. Whether a JVM is a good thing or not, it's a separate question, but it's the best language for JVM, trust me. And I tried a lot of them, it's the best language for JVM. That's true, yes. It's kind of... Java is a very interesting, is in a very interesting position. It's kind of difficult to make a better language for JVM than Java, unless it's Kotlin. Even Kotlin has a really hard time, because every time a new language arrives that is better than Java, Java essentially just steals feature from that language and becomes the better language like for JVM. So yeah. As soon as Scala appeared in JVM, like Java instantly got all of these beautiful function programming features. So yeah. All right. Though I haven't programmed in Jira for Amsterdam, so I don't know. Anyways, so what I want you to do, I want to do this similar thing here, just basically execute until I get to the right consistency. Right, there we go. So I got to the right consistency, I have the machine. And what I want to do here is I want to return the boundary. So I'm going to return W2. And can I get the minimum? So I'm going to go to the Google. And it's going to be data set. Min max. Yeah, we can do something like find min. Well, as well, actually, you know what? Just return this machine and just play a little bit with that machine. Or no, this is a this is a state. So this is going to be just a state. Okay. So let me give it a try. So in state, I get the black panels, and then I try to find minimum, right? So I'm trying to find the minimum, and that should give me V2, right? Is it gonna be the right thing I want here? All right. So find min, and let's try to execute this thing on the part 2. It should give me like the minimum here. Is it really the minimum? Is there like smaller? If I do something like V2 minus 38, is it less than this thing? It is less, so that means it's the minimum. It's the minimist. Alright, so we can also check out the maximum, the maximist. Find max among the black panels. So we're gonna do that trick, and it didn't work. Thank you very much. Thank you. Very cool. Boom. This is not what I wanted. I wanted to do this thing. It's not that big, actually, if you think about it. So the range is actually quite small. Okay, so this is X. And this is the maximum. So from that to that, but this is in reverse. This is in reversed order, right? So I guess that's okay. To be fair, I can just do from minus 100 to 100 and be done with it. So yeah, that's how I'm gonna deal about that. All right, so we're gonna start with the row. Row is gonna be from minus 100 to 100, minus 100 to 100. So since it's a row, it's going to be just y then, and then we're going to have this thing from minus 100 to 100 as well. And essentially, right, essentially, we need to do that a little bit carefully. So we have to have like a nested list comprehension, unfortunately. So it has to be a nested one. Really sorry, chat. It is what it is, and it isn't what it isn't. So if x, y, as member of the list of the black things, it's gonna be actually replaced with dot. Otherwise, it has to be then. So it's gonna be like this. Cool. So that's a very strange way of doing this thing, but okay. Maybe if I wrap it in parentheses like that, it's actually way better. This is a valid Haskell, by the way. Okay, so and then I can do unlines to turn it into like a single string, and I can just return it as a string, and the only thing I need to do here is just to print the string, so that's gonna be it. Shut. Are you ready? You are not ready because I'm not ready. So bs is equal to black panels for the state. There we go. And it is done. Okay, so I was gonna do this thing for a while, and it's not gonna print anything readable right now, right? Because I'm really sorry for this stuff. So what we need to do here is now put strln. Okay. Something went wrong, definitely. So it did the trick, it did the thing, but it doesn't look like anything. Alright. If it's in there, actually, that's really weird. So it... So if the color is black, I insert it into the blacks, and then that's really weird. What the fuck? I'm pretty sure I'm doing everything correctly, but... Okay, and what do we expect? 8 capital letters, okay. Based on the space law brochure that depends... A valid registration number is always a 8 number after starting orbit on a single white panel. Instead, what registration number does it paint? Maybe the registration number is actually painted somewhere there. Nothing looks like a registration number here. Unless like in somewhere here. But yeah, it's actually... Yeah, I'm really sorry for the quality. Let's think, where did I make a mistake? So you start on a... Oh shit, yes. Ah, fuck. Okay. So we need to provide the default color. I think I know. So this is gonna be like this. Default color. Yeah, so this is the default color. So panel member of... This one is interesting. Okay, so depending on this one, so case a default color of. If the default color is black, right? If the default color is black, this is a valid thing. This is a valid thing. Otherwise, we're gonna do that slightly differently. So we have to switch to this thing. And how do we... Yeah, so if it's part of this thing, it has to be 0 or 1. Okay. Thank you for the rate, Coffee C 25. So I'm just trying to think if my logic is correct here. So do we use WS anywhere here? No, we don't. Yeah, okay, so that makes sense. If the default color is black, we look at the whites. If the white is, if the member isn't part of the white, it becomes 1, 0. If the default one is white, we take a look at the position at BS. It should be 0. It should be 1. Okay. Let me see. Should be okay now. Okay. Make machine. Okay, so the next state. So for the part one, the default value is gonna be black, right? So it's gonna be black. For the part two, the default value is gonna be white. So this is how we're gonna distinguish between them. This is how we distinguish between them. All right, let's give it a try. There we go. So we got it. One more time. Cool. So I need to type it now somehow. Oh shit. Oh my god. Okay, just a second, chat. I'm really sorry for the bitrate. I cannot do anything about that. L-E-V-E. Cool. So, alright. So this is the output, right? So this is the output. I might as well actually start the output from like 0 to 100. So maybe it's gonna be a little bit better. Yeah, we're gonna start from 0. And let's give it a try. So does it fit even there? Yeah, it does fit there. So I think I can even make it smaller then. It just depends on the size of this entire thing. Emacs. Doesn't let me quickly jump between all of this shit. Maybe like around this. 44. So in terms of y, it could be like 50, right? So in terms of y, it's 50. 1, 2, 3, 4, 5, 6, 7, something, something. It could be like 7. Cool. So now, if I just do that, and of course, if I redo that, I completely fucked up because it has to be 57, of course. So let's do it like this now, one more time, and there we go. We can see the output. I think it's pretty cool. I think it's you. Maybe it is you. Yes, it is you. Okay, chat. Are you fucking ready? So stat prediction. So previous predictions. First try got cooler. First try pog. So what's gonna be the alternative result? What's gonna be the alternative? Who can come up with a funny alternative outcome? PPG club. All right. So we're gonna take a minute, right? So it's gonna be like 1 minute. First try pog. PPG club. Stat prediction. Got it. I think I should probably tick this thing here so it doesn't show it again, but I'm afraid that I may miss something. So yeah, place your bets, chat. Are we gonna first try this beer or not? We'll see, we'll see. No doubters. Really? Can we take a look at the current results? Ah, interesting. Interesting. So, but we do have a little bit of a doubters situation going on. Interesting. Oh, some people are doubting. Holy shit. But you guys do understand that you may lose the point. I mean, yeah. What if it's gonna be first try? You're gonna literally lose your points. So, all right. Let's go and submit the result. Let me double check. So, UGB, HLE, UV. All right. So that's the final result. All right, and doubters, doubters. First try. First try. Got good. Doubters get wrecked. Doubters get wrecked. All right, that's pretty cool. So that's what you get for being a doubter. Yes. All right. So let's actually clean everything up. Now, let's go. It's gonna be a machine. So I think I'm gonna just read machine from file. Is this how we do that? I'm not sure. Read. Maybe it's just called machine from file. Machine from file is gonna be input.txt. And then we're gonna have part 1, right? So we're gonna just provide the machine. So this thing shouldn't, yeah, it doesn't do any side effects, so that means we can just do something like this. Part 1, and it's gonna be just D. Yep. So afterwards, printf part 2, and it's gonna be a new line, and after that we're gonna do put strlen. Yeah. Part 2 machine. Cool. Let me try to do that, and we don't have a printf because we need to import text printf. Cool. And if I try to just run this entire thing, so part 1 is going to be one thing, and part 2 is going to be just that. It's kind of quite surprising how part 2 is faster. Oh shit! They're doing the same thing, but part 2 is faster. Who knows why? Who knows why it is faster? In part 2, we never touch detached panels, so that means they are never calculated. Oh shit! That's actually so funny. Yes. So yeah, because since you never need them, right? And it's a pretty big. It's a pretty big set, so it's never actually computed. So that's pretty cool. Laziness strikes yet again. How about that? Cool. Haskell lazy. Poker. Yesu, kawaii. Now. What I want to do, I want you to create like a readme thingy. Okay, so I'm gonna go in here, and it's gonna be a readme md day 11, and yeah. So let's actually put it like that. Day 11 solution. This is what we're gonna have here, and expected result. It's gonna be console. Like this, and we're gonna literally just put this thing here. So this is gonna be the expected result of ours. And we also have a little bit of modification for the int code machine. But yeah. So the 11 add day 11 solution, and let's push that right at the repo. Absolutely fucking epic, mate. So let's create a folder for the day 12. How about that? Let's create a folder for the day 12. It's going to be module main where. It's just this thing. Usually there is a problem, like one problem. So far I noticed the pattern, right? One problem, one day is int code related problem, another day is not int code related problem. So probably day 12 is not going to be int code related, so it's probably going to be something else. So we need to prepare for that. So yeah. Oh, what was that supposed to be? Probably some sort of station or whatnot. Okay. So before we're gonna continue this entire stuff, I want to make a small break and pee. All right. Small break. 2 minutes. I think 2 minutes should be enough. Should be enough for everyone to pee. All right. Okay. Let's make a small break. And you guys have fun. Yo, what's up? Welcome back. So, Yesu, kawai desu. Day 12. Are you guys ready? Let's just jump into it. The end, for fuck's sake. The end body problem, holy shit. Do I really have to implement the end body problem? Is that a spoiler? It's probably a fucking spoiler. Alright, sure. I love end body problems. Okay. The space near Jupiter is not a very safe place. You need to be careful of big distracting red spot. I see. Great red spot. Yeah, this one. I see. We have to be. So the size of the diameter of this spot is actually bigger than the diameter of Earth. Right. Is there like any comparison? Yeah. So this is the size of the Earth, and this spot is actually like bigger than Earth. Holy shit. Yeah. Classic. Extreme radiation and a whole lot of moons swirling around. Yeah, Jupiter has a shit ton of moons. Oh, by the way, so yeah, so there's a huge radiation like magnetosphere of Jupiter. Whatever. Well, the moons swirling around. You decide to start by tracking the 4 largest moon: Io, Europa, Ganymede, and Callisto. I don't know how to pronounce this name. I'm really sorry. I know how to pronounce Io, but probably Europa is just pronounced like that. After a brief scan, you calculate the position of each moon. You puzzle input. You just need to simulate their motion. You need to, so you can avoid them. Each moon has a 3-dimension. Oh shit! And body in 3 dimensions. Holy fuck! Okay, so this is the last problem for today. That's for sure. Last problem, by the way. The position of each moon. You just need to simulate the. Okay, so 3-dimensional velocity. The position of each moon is given in. You scan the XYZ velocity of each moon starts at 0. Simulate the motion of the moons in time steps. Within each time step, first update the velocity of each moon by applying gravity. Then, once all moons' velocities have been updated, update the position of every moon by applying velocity. Time progresses by 1 step once all of the positions are updated. What is the time step though? 5 hours problem, yes, that's what it is. It's the 5 hours problems. To apply gravity, consider every pair of moon. On each axis XYZ, the velocity of each moon changes by exactly +1 - 1 to pull the moons together. However, if Ganymede has an x position of 3 and Callisto has an x position of 5, then Ganymede x position changes by +1 because 5 is greater than 3 and okay. However, if the position of the given axis are the same, the velocity of this axis don't change for that pair of moons. Once all gravities has been applied, apply velocity. Simply add the velocity to each moon to its own position. For example, if Europa has a position of 1 to 3, the velocity then... Oh, okay, so the velocity is a single time stamp. I see, it's a time step, not time stamp. Step. This process does not modify the velocity of any moon. Alright, for example, suppose your scan reveals the following positions. Okay, simulating the motions, blah blah blah, pretty straightforward, I guess. Then it might help to calculate the total energy in the system. Okay, the total energy for a single moon is its potential energy multiplied by its kinetic energy. A moon's potential energy is the sum of the absolute values of its XYZ position coordinates. A moon's kinetic energy is the sum of the absolute of its velocity coordinates. Okay, below each line shows the calculation of a moon's potential energy and kinetic energy and total energy. Okay. In the above example, adding together the total energy for all moons after 10 steps produces the total energy in the system 179. Second example. So, do I have to just... What's the... Ah, okay. After simulated in scan for 1000 steps. Okay. That actually sounds interesting. It may not even involve floating points, which is nice. So it's purely in integers. Oh shit, okay. You apply the gravity. For example, so on each axis, the velocity of each moon changes by exactly +y to pull the moons together. For example, it has a... So I still didn't understand the gravity part, right? So we'll probably have to figure it out that a little bit later. But apart from that, is just, you know, yeah. So you have a position of the moon. You essentially have 4 moons, right? 4 moons, and you have a function that simulates one step, and you repeat that function thousands of times, and then it's pretty straightforward. It's pretty straightforward, not just gonna lie. Okay, so let's introduce data v3. v3 is gonna be int, deriving, so I'm gonna make it showable. I'm also, just in case, gonna do equal and ord, and yeah, there we go. So then we want to introduce something like system, and the system is basically a bunch of these moons, right? System, right, and it's gonna be moons, so it's gonna be a list of v3, right? It's gonna be a list of v3. And as far as I know, the input is actually here. So here are the... Oh, you also have to parse this approach. Come on, dude, seriously? Come on. But okay, sure. So essentially you just... Yeah, cool. So this is going to be input txt. There we go. So parse v3, so it accepts a string and returns you v3. Okay, so we'll have to implement it a little bit later. Undefined parse v3. So we also want to have like a kinetic energy. What the fuck is going on? Holy shit! Stop. All right. So there's a kinetic energy, there's potential energy, kin energy. So total energy is the total energy of a single, is a potential. Total energy for a single moon is its potential energy. Okay, so maybe I'm not gonna go there yet. So we're gonna have a step, system, or maybe simulate. It takes a system and produces a new system, right? Okay, system and produces a new system, and there we have a system. Cool. Nice. We need to apply the gravity. To apply gravity, consider every pair of moon. Okay. On each axis, the velocity of each moon changes by exactly +1 or -1 to pull the moons together. Position of X and Callisto position of 5, then velocity changes by +1. Alright, so we're considering each pair of the moon. And we change their velocity simultaneously. But does the order matter? Order doesn't matter because we're changing the velocities, we don't change the positions, and positions is the only thing that we take into account while making the decision. Okay, makes sense. So I need a better way of iterating pairs. Because right now I know of a relatively crappy way of iterating pairs. I need something better. So let me see what we can do about that. Imagine that you have something like this, right? From 1 to 5, and this is not particularly what I wanted. I wanted something like this, right? So I want to access. So one way to iterate the pairs is essentially by doing something like A in axis and B in axis, and here are your pairs, but it creates duplicates. So in our case, we want to avoid this kind of duplicates, right? In our case, we want to avoid this kind of duplicates. So I was thinking how we can actually avoid that. For example, the duplicate is going to be 1, 5 and 5, 1, right? So one way is that you can employ a function, right, that basically does the following thing. So we can have a/b. If a/b less than b, then you swap them around. Actually, let's put it the other way, right? You swap them around. Otherwise, you keep them as they are, right? So, and then you sort everything here. Of course, you cannot do that unless you actually imported this entire thing. You sort everything, and maybe you don't even need to sort anything. You can just use none, and that gets rid of all of these duplicates. But if you, I guess for our case, it is a good thing. I think for our case, it is a good thing. Kafesi, you're working with indices, you don't work with values. Okay. So I think there should be easier way. I think there is a thing called tails, right? So essentially, you can work with something like this, right? So which may simplify this thing. I can filter them out as well, sure. It's probably even easier. Okay. So yeah, filtering them out. Yeah, filter less or equal, right? So only leave those that are less or equal. That's a pretty good idea. Yeah. But it's all works for indices. Holy shit. Like, so many people fall into that trap, right? So it works for indices. We're not doing indices, we're doing values, people. But you can sort them, but come on. People, use your brain. Stop, use your brain. Okay, so essentially we probably want to use something like tails, right? And tails could be relatively useful. Okay, so first we are iterating. Yeah, and you'll have to take the head of it. So let me think what's going to be the best way to do that. You have axis, and then you're iterating tails of axis, right? You're iterating. Maybe I should put it like this. So it's going to be a. So here's the tails of axis, and within this thing, you iterate in this thing. here's an interesting thing. It also gives you empty list, which you don't really want to do. So maybe it also makes sense to filter not null, so you get rid of that stuff, because you don't really need that. Then we're iterating through each element here, and our result is essentially head of A and B, and that worked perfectly. And by the way, people, this works with elements, not indices. Not indices. All right. So yeah, this is how we're gonna do that. Cool. So we just iterate through the tails, and each tail, blah blah blah. I wonder if you remove the filter, right? It will crash. It should crash actually. It doesn't crash. Huh. I wonder why. Oh, because you're trying to iterate for like the empty one, and it doesn't produce anything. Okay, that makes sense. Yeah, that makes sense. Cool. That's actually pretty cool. All right, so that's one way to iterate all of the pairs. Cool. Not the indices, values, not the indices. Everyone wants to iterate the indices. We don't need to iterate the indices. Okay. Okay. Cool. Now. We can even like turn it into some sort of function. I mean, why not? Players. Right. We accept this thing, and we actually get this thing. We can even call it unique players, right? Unique. I'm gonna call it like this. Unique players. And here we have A and B, and I'm gonna just do it like that. There we go. Cool. So does it include when the things are equal? Yeah, it does include the things that are equal. Perfect. Yep. And you also... Oh, shit. But you don't need to include the things that are equal, actually. Yeah. You know what? I think it has to be like this. It has to be tail of A. And yeah, at some point you'll also have to do something like this. A, not null A. Not null A. There we go. 1, 2, 1, 3. Yeah. Aha, perfect. This is what I wanted to do. So yeah, that's what we want to do here. So we have first A and then that one. So should be perfect. I should remember this pattern, by the way, because it quite often I need to do that in Haskell, and I keep forgetting how to do that. Why am I copy pasting this? I wanted to copy paste this thing. I wanted to copy paste this thing. Cool. So unique pairs. Now in our case we're not gonna have any other pairs, so we're gonna only have these kind of pairs. Cool. So we need to consider all of the pairs of all of the smooths. Oh shit, and that's kind of annoying. So we still need to iterate the indices or not? Is there a better way to do that without going into the indices? Yes, kawaii desu. Yeah, because it's annoying. This is a very annoying problem to solve in Haskell because it's a very stateful one. It's a very annoying problem to solve in Haskell. Because, yeah, so you have the amount of moons, you iterate pairs of indices, and then you update them back. And so basically you also need a way to address those pairs in an O of one way. So, yeah, it's very annoying. It's very, very annoying. So I'm gonna make a cup of tea. Does anyone have any questions while making a cup of tea? So the thing is, like, can we avoid this idea of having a state of these moons and iterating the list of pairs of indices and constantly updating that state? Is it something that could be avoided? It would be actually pretty cool. It would be actually kind of cool, because essentially yeah, I think you can do that. So you can take one moon, right? You can take one moon, right, X, and the rest of them, right? Yeah, essentially you need to generate a list for each moon, and the list that doesn't contain them, right? And that will be enough for you to calculate. But this is essentially what the pairs of listed does, right? But that means we'll have to also provide the indices and whatnot. I guess that's what we'll have to do. So we have in this thing. I think I got an idea of like roughly how to implement that. Alright, no questions, cool. I'm gonna go to the kitchen and boil up some water. Cool. So we're back. Essentially, what we need to do here. So it would be kind of cool to have things like hello, right? And then we need to index this. So this is how we're gonna do that. This is how we index them, and which makes it relatively easy to remove a very specific thing, right? It makes it relatively easy. So we can save that to here. So it's something like this. S is going to be hello, right? And axis is going to be S of that, right? S and indexed, S and indexed. So, but maybe we don't need that. So I want to map each individual axis here. I actually want to... Yeah, I do want to map it. And how I'm going to map it? I'm going to have an index index, and I don't care about this thing, and then I take axes yet again, and then I can just basically filter out something where the first is not equal to I. Right, the first is not equal to I, and there we go. So on the first one I don't have a hello, on the next one I don't have E, and then L, and so on and so forth. And that should help me to actually iterate music. Is there something wrong with music? I don't understand. Is everything okay? I don't even know what that word means, I'm sorry. Okay, so I think my tea is ready. All right. Okay, cool. Now, we can employ this technique. So, and here, essentially, we have the current one for which we're computing everything, and the result of the filter is the rest of the moons for which we have to do the thing. Yeah, and we don't have to even worry about modifying the rest of them, because the rest of them are going to be modified automatically. So that's pretty cool. All right, and so what that means, we don't need any of this shit. Okay, so I figured it out. Nice. So we need a function that takes a single moon. We might as well introduce a type def called moon v3, and we have a bunch of moons, and so on and so forth. So we're gonna call apply gravity. So it takes the first moon, the second moon, and returns the first moon with applied gravity according to that moon. All right, so let's do it like this. So apply gravity, so moon A and moon B, and we have two conditions here, right? So has a position and has a position velocity. And we need to iterate through all of their like positions X, Y, and Z. So this one is very interesting. Okay, so and let's introduce that. So this is going to be X prime, Y prime, and Z prime, right? And let's compute them separately. So X is going to be the following way. If you know what? I think we can destructurize them like right here. X1, Y1, Z1 V2, X2, Y2, Z2. And if X1 is less than X2, what's gonna happen? So if the position of this thing is 3 and the position of this thing is 5, the position of X changes by +1. So if the position of first one is less, that means its velocity. Oh shit, yeah. So moons also have velocities. I completely forgot about that. All right, so that means it's more complicated than I thought. Moon position is gonna be this thing, and then we also have moon velocity. Vector 3. So this is basically what we're trying to achieve here, and the final result is going to be a little bit more sophisticated than this. Gravity does not modify the position, so we don't even have to worry about that. So moon 1, moon 2. So and what we're doing here, we're modifying moon 1, and we're modifying its velocity, moon velocity. It's gonna be V3, 1, 2, 3. So, and this entire thing is actually like really depends on these conditions. If we need an easy way to destructurize all of that. I think we need an easy way to destructurize all of that, but I'm not 100% sure. Yeah. Are you guys still talking about indices? I already solved the problem with indices. Why are you guys still talking about that? Let's talk about how to apply gravity. So the indices has already solved the problem, don't worry about it. So how do we apply gravity, and how do we not drown in the complexity of pattern matching and destructurizing? That's a more interesting question. Alright. Bike shading, am I right? Okay, so here is moon position, and how we're gonna do that? We probably apply no. Gravity has nothing to do with indices. x1, x2, y1, z1. Alright, so we can do it like that. And we also need to know the velocity, so this one is kind of complicated, not gonna lie. So it would be kind of cool if the vector 3 was also traversable. If it was also traversable, because I would probably simplify a lot of other things. You don't understand the problem? I can actually give you the link. Here's the problem. Jia Yang, welcome to the stream. Hello, how are you doing? How was your day? So we're doing Advent of Code, the n-body problem thingy. I'm starting feels every day. Yeah, I noticed you look a little bit more down than usual these days. I hope everything is okay. Seriously. Alright, so let me take a look. Still okay for now. Okay, cool. Stay strong. Right, so I think I need to update this thing. So just relax and enjoy a cozy Advent of Code stream, or cozy Haskell programming. Yep. Cool. Yeah, so this problem is really interesting because it requires you to keep track of a lot of state and stuff like that. Okay, so I guess we need to just shave the yuck and just do this thing. Relax in Haskell. Well, why not? So, to be fair, I find programming in Haskell pretty relaxing, especially if you know what you're doing, right? So if you know what you're doing, it's like you're building, like you're solving a puzzle pieces, putting together. Yeah. So for me, Haskell is not particularly useful language for real-world applications, but it's really good for recreational programming, for programming just for the sake of programming. I think it's quite good for that. Vx1, then Vy1, Vz1. So we're gonna have something like this. And for the moon2, since we're not modifying the moon2, I'm not gonna keep the add pattern for it. So, and this one is gonna be just 2. Chill out with Haskell. Right. Okay. So, this is not particularly good, but it is what it is. I can't do much about it. If x1 less than x2, right? So, as we know, if it's less, right, if the x position is less, that means its velocity is changing by 1. So that means Vx1 has to be +1, right? Otherwise, if so yeah, we need to do this like several conditions, and I wonder what's going to be the easiest way to do that. But maybe if we had like some sort of a special function that accepts 3 integers, right? Integer, 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 we could do it. x1, x2, and just v, right? So, and if x1 less than x2, then v plus 1. If it's greater, then it's minus 1, and then otherwise is going to be the same. So this is basically the function I want to have. And then I want to just apply to x1, x2, vx1, right? And just forget about it, like this. So I might as well actually put it under where? Under where? You know, all the expressions here are called underwear expressions. Funny, I'm sorry. Alright, so please don't ban me, chat. So then f, y1, y2, v, y1. I'm sorry. Okay, f, z1. Actually, wait. y1, y2, z1, z2, v, z2. And it's really easy to make a mistake here. So here's the axis, y1, y2, y2, and this has to be 1 actually. Alright, so that's essentially what we do here. Do we not? I think. And by the way, we can change the ordering of this entire stuff. So essentially we can put v as the first thing here. And of course that will require changing the ordering here, right? Like this. Right, so, and then, I don't think it changes anything particularly. So I was thinking maybe if you make vectors 3 traversable, you'll be able to utilize like zip something. But does zip even work with traversable? It doesn't even work with traversable, so there. But apart from that, yeah. So how do we call this f function? We can call it gravity actually. So this thing could be called gravity. Gravity. And since it has such a generic name, maybe we can do it like that. Gravity, and then I'm gonna quickly do it like this. Gravity. Yeah, boy. Alright, so this is completely unreadable. I wish I could make it more readable, but I cannot make it more readable. Excuse me. Well, I can extract that. Okay, so this one, by the way, has to take like 3 of these things. It has to take 3 of these things. What I want to do now, I want to make it work with lists of these integers, or with W3s. Yeah, so we can call it gravity 3, and this is going to be just this then. So it's basically the same thing, but for the vectors. And I wonder if you can make it more like generic or whatnot. And obviously this one is essentially just doing it like that with 3. So let me put this entire thing here. So this is first one, this one is going to be the second one, it's going to be the second one, and then I need to take the velocity. Right, I need to take the velocity, but for this specific velocity we don't need to distinguish between 1 and 2 or anything like that, it doesn't matter. I don't even use the second velocity, like why the fuck am I doing that? Right, so yeah. And here, what we're doing is just this. Alright. Yeah, there we go. So it's basically this, but for 3-dimensional vectors. And the question is, how can you simplify this entire stuff. So we have this. I think it's literally zip with 3. Yeah, that's what it is. Okay, I see. I think it's literally zip with 3. Okay, I want to remove apply gravity because I think I would be able to actually simplify this entire stuff dramatically. Okay, so gravity. So first thing is the velocity. It takes the velocity as the first thing. Let's put 69 here, and then the x and y, right? And then depending on their values, it basically makes a decision whether to do +1 or -1, and if they are equal, it leaves it unchanged. So this entire thing also works for vector 3s, but it works on the level of several components. So essentially what it does, right, it does zip with 3 if you treat vector as a list, right? So, but unfortunately zip with 3 doesn't work with traversable, so it works with lists like that. So let me see. Is there a function that works with traversable? Traversable. So there's data traversable. Okay, so maybe I should take a look at that module. This module looks very interesting. I think it's going to be super useful for our case. Do you have zip? So there's a zip list, but not really. I really want to have a traversable that works with zip, zips that work with traversable. Unfortunately, they all work with lists, which is kind of sad. Okay. Oh, I need to wait until the page is loaded. Okay, cool. So we can do... Oh my god. This page is the worst. So it's a traversable, it traverses the things, and... Oh, maybe, by the way... So zip works with sequences. Haskell traversable zip. What's the most standard generic way to zip a traversable? Okay. Map accum. Okay, so there's a thing called map accum L and map accum B. Function behaves like a combination of a map and folder. How does it solve anything? Okay, map accum pair. It's really weird. Yeah, it's kind of strange that traversable is not like really zippable and you have to go through all of this weird stuff. Because the thing is, if we had just zip for traversable, I could implement gravity v3 as, well, I mean, it would have the same signature, right? So it would have the same signature. It would be something like gravity 3 zip with 3 gravity. Seriously, if I could implement traversable interface for v3 and we had a zip for traversable, I would implement this gravity 3 like that and just remove this entire thing. You see what I mean? You see what I'm trying to do here? Because this is literally what it does. It just doesn't do anything else. So one way to probably solve that is to convert traversable to list, zip the list, and then convert it back to traversable. But I'm not sure if traversable actually provides any of this. Like, this is really inconvenient, not gonna lie. So let me see. Like, why this is not a thing? Traversable, right? So traversable, yeah, you can sequence that, and there's no really way. Like, why? Why there's so little stuff for traversables? Does anyone understand what I'm talking about? And does anyone know a solution for that? Or maybe we need foldable instead? By the way, what does foldable do? Foldable. Why Haskell standard library is so pepega? Okay, I see. Like, I mean, I already found the answer, just do it yourself. I was thinking maybe somebody knows anything else. Like, I mean, I know that I can write it myself. Sure, like this is literally that what I've got here. Like, just write it yourself. So this change. Okay, I guess I'm just not gonna care then. So, so it's gonna be moon 1, moon 3, moon 2. Right, and then what I'm doing here is I'm setting moon 1 to moon position. So moon velocity, right? So it gives me moon velocity. Alright, and what I put here is gravity v3, moon velocity of. I can probably destructurize it like that. So it's gonna be moon 1, moon velocity vel1. This one has to be moon vel2. Alright, so we have vel1 and vel2. And you also need the position, so that's quite important. So moon pose 1. Right, so this is one thing. And also moon pose 2. Alright, moon 1. So we provide the velocity 1, the one that you want to modify, velocity 1. Then you provide position 1 and position 2. And that gives you the result, which is still too long. This entire stuff is still too long. So probably because of that, I want to maybe inline all of this stuff. So it's going to be something like moon velocity moon 1. Here we're going to have moon position moon 1. And then moon position moon 2, and just get rid of all of that. Yeah, moon 2. Okay, we applied gravity to a single moon according to the second moon. All right, so it seems good. Cool. So it doesn't compile because why? Oh, yeah, I'm an idiot. So gravity 3 duplicate. Yeah. So it's impossible to implement it like that. Okay, cool. This is more or less readable now, right? This is more or less readable. Like, I was trying to simplify, like reduce the complexity of this entire stuff, but yeah. Bot year. All right. So after that, we have a bunch of moons, and we need to apply the gravity to them. So, but we have to apply them according to the stuff. All right, apply gravity. So this one is a moon, right? So I'm gonna do. Oh shit! Huh? I have an idea. I'm gonna call it gravity moon. So yeah. That is really funny. So we have rules for applying gravity, and we're starting with a single component. This is how we apply gravity on the level of a single component. This is how we apply the gravity on a single vector. This is how we apply the gravity for a moon. And then we're going to have a gravity system, which takes a system and applies the gravity to all of the moons within the system. So you see, we're starting from... This is actually works out really nice. Really like that. Ah, nice. That's actually pretty funny. And the way we're gonna do all of that, right? So maybe we're gonna have like, yeah. So here are the moons. I'm gonna call it moons ms like this, moons ms. We're gonna zip everything like this, and that gives us indexed moons. It gives us indexed moons. All right. After that, I have to do a map of all of these things. So, and here I have my own index, and I have the current moon, right? I have my own index and I have the current moon. So on top of that, like, I need to probably save all of that. Yeah, I'm gonna have indexed moons. This is what we're gonna call it. Indexed moons is what? It's gonna be like that. Zip 0 system moons of the system, right? So here's the index moons, and there we go. So then I want to take filter FST of indexed moons, all of them that are not equal to ID, and there we go. So I have a list of these moons in here, and now I'm about to fold the shit out of them, because this gravity moon thing essentially uses the first argument as an accumulator, and it accumulates all of these moons in here. So it works out fucking perfectly. I really love it. I really love it. So fold left, right? Fold left. So the fold function is gravity moon. The fold function is gravity moon, and the initial position is the moon itself. There we go. So this is how we do that. Amazing. Indexed moon, and we can also just do something like remove index. Alright, and this is gonna be this thing. So filter everything, and this is gonna be I. So indexed moons, I can then say remove index I, and then fold gravity moons. It works out beautiful. So now I can easily apply the gravity to the entire system. Cool. And this is how much code it took in Haskell. To apply gravity in the entire system in Haskell, you need 22 lines of code and 4 functions. I mean, yeah, I could smash them all together, but then it will be very difficult to keep track of the things. So this entire code, these 22 lines of code, are just to apply gravity to the system. Because you need to consider all of the pairs, right? You need to consider all of the pairs when you need to accumulate things, and yeah. But I think it's concise and as readable as I can get it, right? Yeah. So first function applies the gravity to a single component of the vector. The second function applies gravity to a vector, and the third function applies the gravity to the moon, and the fourth one applies the gravity to the system. So we're just building up the system. Building up the system. Okay, that's pretty cool, and hopefully all of that will compile. It doesn't even compile. Great. So all right, remove I index. So moon integer. So it fails somewhere at 40. Right, so, oh yeah, okay, and you map all of that, and yeah, so it basically gives you this stuff, and you need to replace moons string. So you need to first strip off all of these things, right? So here's your first function. You also need to remove the index, and maybe you also want to map it with SND. Yeah, this is probably what I forgot. Okay, that makes sense. Alright, and now it fails that you return a list of moons instead of the system, so that means you have to do something like system moons equal this thing. There we go. So system moons equal to this expression, and now everything compiles. It would be nice to actually extract this entire stuff into something more readable. Yeah, I could probably take this fold thing and turn it into something, but I don't think it's actually worth it. So this is applying gravity to the whole system, and all of that compiles. Nice. All right, so the next thing, so time steps. Then once all moon's velocities have been updated, update the positions of every moon by applying velocity. Okay, time progresses by one step once all the positions are updated. Okay, so once all gravity has been applied, apply velocity, simply add the velocity of each moon to its own position. Okay, so it's gonna be velocity moon, right? It accepts the moon and returns a new moon. There we go. So how are we gonna do that? I think we need to implement a plus thingy, right? So we need to implement a plus operation for the vectors. So it's gonna be like this: plus vector 3, another vector 3, and the result is gonna be vector 3. So it's gonna be something like this. Vector 3. I'm just thinking x, y, z, and vector 3 is going to be a, b, c. This is actually a very interesting idea. X plus a, y plus b, z plus c. So essentially you won't confuse numbers anymore. You won't confuse them. But yeah, anyway. Velocity moon. So essentially what you do here, it's a moon, moon position, and then moon velocity, right? And then what we're doing, we're updating the moon velocity, actually moon position, right? By taking its position and adding the velocity. There we go. So we updated the velocity of a single moon with a very kawaii operator. This one. Okay, so now we need to do a velocity for the whole system. So it's going to be velocity system, and it takes the system and produces a new system. So system moons equal moons system map velocity moons, like this. So this is how we apply velocity to the whole system. So essentially you have a step that applies gravity to the system, then you have a step that applies velocity to the system. So then we can have something like step system that takes a system and produces another system. And what it essentially does, it's a composition of gravity system and velocity system. Right. So this single function takes the system of the moons, applies the gravity and applies the velocity. So steps. Fucking David chat. Come on. All right. So let's see if this entire thing compiles. It does compile. Okay, so, and what we need to do here, we need to take the initial state of the system, right? We need to take the initial state of the system and perform that shit thousands of times, right? And then we also need to calculate the energy and whatnot. Oh shit, yeah. Okay, so now we need to learn how to parse the vectors, right? Because this is what we're gonna have in the input. Okay, so is there any way, like you can always split by comma space, right? You can always split by comma space, but you'll probably need text shit. So yeah, let's import text shit. Import data, actually qualified data text st. And I also want to probably enable the extension language overloaded strings. So this is what we're going to have here. Overloaded strings. So, and in here I can split on, right? I can split on. Where is my input here? There we go. So here's the input, and I can split on this thing. So, and that gives me that. But the problem is that this thing consists of this shit, and it's very annoying. So can I do substring or slice? So I want to be able to take slices of the text. Let me find any information about that. So text package. Text package should have some stuff. Is there any slicing going on? So substring. Okay, so you can do substring. Okay, there we go. Substrings. You can take shit, drop while, strip start, strip end, remove leading white spaces. Okay. Drop around. Returns a substring remaining after dropping characters that satisfy the predicate from both. Oh, this is actually perfect. Can I do something like that? Drop around. So you have to provide the predicates. Right. So, and this thing should be equal to this or equal to that. Is there any way in Haskell to take these two functions and combine them in terms of OR? Alright, so you can treat the functions as monads. So you can try to lift to M. Holy shit! Wait a second. Is that a divine intellect? Control monads. Oh shit, I think I'm overcomplicating it, of course. I'm overcomplicating it because you can always do something like member, right? Right, member. Yeah, so in this function essentially tells you whether this thing is that or not that, right? So essentially any function is a monad, right? Any function that has one argument. So it's a monad by its result. It's a monad by its result. So that means you can do, you know, all of the monadic operations on it. So, and you can combine the results of two functions here. So here's the first function, here's the second one, and you combine them by OR, and that basically composes the two functions. But I'm not sure if it's a good idea, because you have functions like member that check if you have a value in a list, right? So it's a member, I think, contains, I don't remember, is it a member or something else? Member. Data list. Member. I forgot how it's called. I literally forgot how this function calls. So a boolean. Come on. Why is it hanging? Holy shit, why is it hanging? Wait. Is the... Okay, LM, holy shit. Sometimes it's called member, sometimes it's called LM. Holy fucking shit. Okay, so, and this is what I'm... Because you can replace this monstrosity with just something like... so LM, so it accepts this as the first thing. Okay, so we have to do it like that then. LM, this, right. So, and that already gives you the same function that checks whether this thing is that. So you don't need that monadic divine intellect, right? You don't need that monadic divine intellect. So you can just do that. You just check that value is you know, part of that list or not. So and that's way simpler in my opinion. Okay, so around, right? So we're doing around. Strip around. Was it strip around? I already forgot how this function was called. Drop around. All right. Drop around. LM. All right, and then we have to take that sample. Right, so we have to take that one and put it somewhere. Oh my god, my mouse is actually dying. It double clicks. My mouse double clicks like crazy. Okay, we did this. Nice. So yeah, it's actually relatively easy. Now I can split on this shit, right? And there you go. Pretty epic. Then within each individual thing, we can split on equals, right? And it has to be t split on equals, right? And then within each of those things, we can take a first value. We can actually, yeah, we need to take the first one. And there you go. We extracted the numbers, and then I can map all of that and actually read it. Right, and I probably have to hint the type, so it has to be string. Oh, it's actually text, so... But yeah, anyway, we actually managed to extract all of that, so that's what's important. So the specific types and doesn't matter anymore. So this is how we parse this particular format with a single line. Okay, cool. Now let's actually grab this entire thing and turn it into a function that will parse a vector 3. All right, so we already have a function prepared for parse vector 3, so let's actually put it here. So it accepts string. I think it should accept this thing. Yeah. Alrighty, so here is the stuff. We can actually use point-free notation, right? Well, I'm not sure if point-free notation is going to be a great thing for that, so let's actually put it like this. It's going to be input, input, and we're going to put it under where? Sorry. XYZ is going to be 3XYZ. And after that, I can easily just put a read in here. But I'm not sure if I can do something like this. Can I do t-read? I keep forgetting if I can read from texts, to be fair. I keep forgetting about that. So let me take a look at the indices. Read. Can you read? So there is a text read. But yeah, I think it's extremely Pepega. Yeah. So we cannot rely on this shit, unfortunately. So what we'll have to do before we can even read, we have to unpack this thing into a string and only then try to read it into the corresponding values and whatnot. Okay, that's pretty pogue, I'm not gonna lie. Okay, so what do we have here? Ambiguous type, blah blah blah. So element is foldable. Cannot do anything about that. Can we do something like TLM? And there is no such thing as TLM. Alright, so maybe it's located somewhere. It's located in internal... You know what? I'm gonna do it like that. Thank you, Haskell. Very cool. Who can tell me why this works, but this doesn't? Who knows Haskell well enough to tell me why this, that thing doesn't work? Furthermore, string is literally an alias of characters. So that means that this thing and this thing are equivalent to each other. Why? Yeah, so Antoto-Car34 knows about it. Yeah, it's because of the overloaded strings. You guys are right. You guys are right. So yeah, that's exactly the reason. So essentially in Haskell there is a feature called overloaded strings, meaning that the string literals, when that feature is enabled, they're not equal to string. So if you check the type of this thing, it's not a string. It is a something that is a string. So basically it could be anything that implements this interface. So this is what overloaded string means. So they turn string literals not into strings, but into something else, like anything. If I can come up with my own string representation, I just need to implement this interface, and any string literal would be possible to use with my string. So, but that only works if you enable this extension. It's a special GHC extension. And because of that, this kind of thing, like you have to do this kind of shit. Or hint the type. Cozy White Bear, hello, welcome to the stream. So, educational stream, by the way, educational stream. Alright, so let's grab some of these things here. So I'm gonna just take this stuff and parse v3. And there we go, we managed to parse v3. So we're capable of parsing this entire shite. Isn't that amazing? I think it's goddamn amazing. Bruh. Bruh. So I also want to have a function that makes a moon for me. Right, so it accepts the velocity and creates a moon. So essentially the reason why I want to have that is so it automatically sets, yeah, it accepts the position. It automatically sets the velocity to 0. So moon position is gonna be 0, 0, 0. Moon velocity, I'm an idiot. So I'm already tired. What can I say? I'm already tired. I'm really sorry. Alright, so here's that. So you have a position, you have velocity, and now after you parsed everything, you can just make a moon, right? And if you have a list of these, it's not gonna even work because moon is not showable. And if you have a list of these things, you can just construct a system out of that. So this one has to be showable. Right, so it's gonna make a moon, and there we go, we have a moon out of that, and then we can make a system. So maybe we can also do something like system from file, right? System from file. So it accepts file path, performs the side effect, and returns you a whole system. So in the way we're gonna do that, we're gonna, I guess, read the whole file. Once we read the whole file, let's go file path. We split everything by lines. We map each line with v3, right? And right with v3, and make moon, right? So that gives us a bunch of moons, and then we need to build a system out of that. So then I combine that with the system, like this. There we go. So now you would be able to read the system from a file. Alright, so does it compile? It does not, because you also have to do this thing. So you need to import this stuff. Cool. So system from file, and it's going to be input.txt, and system is not printable probably. Yeah, it is not, and you didn't even complain about it. Okay, so cool. So this is our system that we read from the input file. So puzzle input contains the position, right? Puzzle input position of each moon, and when I accept that, I take a position, and everything looks okay. Everything looks okay. Nice. So here's you can read system from the file, and yeah. Okay, do I want to test this on the samples, or do I really go for okay. Here's a second. Okay, so the first example. Oh shit, this is not enough, by the way. It's not enough to learn how to simulate the system and how to parse the input. Next, you need to compute the energy. I almost forgot. So the output is not the state of the system, it's the energy of the system. Yes. God damn it. Holy shit. 5 hours problem, by the way. Yeah, so first we spend time figuring out how to simulate, then how to parse this shit, and now you need to calculate the energy. Thank you, Advent of Code. Very cool. Alright, so total energy. Then it might help to and this is only part 1, by the way. Zozy, why are you still on part 1? It might help to calculate the total energy in the system. The total energy for a single moon is its potential energy multiplied by its kinetic energy. A moon's potential energy is the sum of that. Okay, a moon's kinetic energy is the sum of the values of coordinates. Below each line shows the calculation. Okay, so that makes sense. Cool. Alright, let's introduce a function, energy moon, right? So it's gonna be something like energy moon. It takes the moon and returns the total energy. What we can do here, we can just do it like that. So here's the moon, and I can take moon position plus velocity. I want to be able to like fold the vector and whatnot. I have an idea. Fold v3. Fold v3 plus. This is fucking genius, mate. Moon position, moon velocity. So yes. Okay, so you parse v3, and we can even put something like here. So essentially you accept a function that takes integer and produces you another integer. Then you take a vector and you get an integer. Right, so here's the function, here is the x, y, z, and yeah. Epic. It's kind of an overkill, but I mean, yeah. So we just fold them together, and this is the energy of the moon. Energy system, right? So you take the system, you get the whole energy here. System moon's MS. You map this. Well, you can actually do it like that. So here's the system, moons of the system map with energy moon, and the sum everything up. Here we go. So that's what we need to do here to calculate the energy of the system, and that should be enough. All right. So another interesting thing, we can now define a function part 1 which accepts the system, right? Which accepts the system, and maybe it should accept this step, and then it takes the system and returns you an energy. So what this entire thing does, it takes the amount of steps, the initial state of the system, and then simulates the system n steps, right? It simulates it n steps, and then calculates the total energy of the system. So, and yeah, let's go ahead and do that. So iterate with step system on the system, and that basically simulates the system. So we need to do that 1,000 of times. So n times, not 1,000. So that means we have to do something like this. And afterwards, we need to do energy of the system. Energy system. I said system, please. And there we go. This is as straightforward as I can get it. This is as straightforward as I can get it. So, and it compiles. It's pretty cool. So now we can take some samples and just, you know, test them. Here's a second example. Yeah, so let's do sample 1. Sample 01 txt. Sample 01. Okay, so we have something like this. So this is a sample 01. We're simulating this sample. and the after 10 steps we have this total energy. So pretty cool. System from file sample 01. Okay, so we're gonna do part 1, 10 on that thing, right? And -3. Okay, that's very interesting. Is it absolute? The total energy for a single mole is its potential energy. Ah, multiplied by its kinetic energy. All right, so cool. I don't know why I thought it's gonna be plus. Moon's potential energy is a sum of absolute values. Okay, so also they have to be absolute. Okay, so you know what I'm gonna do? I'm gonna map V3. So, and this already, well, I mean, you can say that V3 is a monad, is a functor, right? Because you want to have a map on it. But I would argue that functor has to be parameterized by a type. So yeah, but you can turn it into a functor. But we don't need to turn it into a functor for our specific case. Right. So if we start generalizing everything, I think we're gonna waste time. So that's why vector 3 is gonna be hard-coded. So here we're gonna have something like this. So it's gonna be that, then we accept vector 3 and vector 3. There we go. So this is gonna be a function, vec 3 x, y, z, and vec 3. I'm thinking it'd be nice somehow. Oh shit, I have an idea. Okay, look. 1, 2, 3. Ah, fuck. Alright, one more time. Boom. Epic. Alright, do we have absolute shit? ABS. It's for number, perfect. So essentially, what we need to do here is... it's kind of interesting, if you ask me. So we have to do fold, actually map v3 ABS like this, and then I'm gonna call it like this. Energy, pause. Energy val, energy v3 int. Perfect. Holy shit, divine intellect. So we have an energy of a single vector, then the whole moon, and then the whole system. And the total energy of a system is actually a sum. Yeah, so this is multiplication and this is a sum. Perfect. That's pretty cool. So, yep. So that's pretty pogue. And this one has to be energy v3. Cool. Now, sample, first sample actually works. Second sample, 02 txt. What about the second sample? So where is the second sample? Here it is. Okay, second sample is gonna be that, but we have to do 100 steps, right? We have to do 100 steps there. So let's actually do 100 steps. 1940, perfect. All right, now input. So let me actually make sure that I have a correct input. Okay, here's my input. There we go. This is a correct input, and what I have to do here is thousands of steps, right? So we need to do thousands of steps. There we go. 7722. Chat, are you ready? Start a prediction. Got Cooder. First try. Dab. Okay, Pepega clap. Alright, 1 minute. I think I should do it like that. Got it. Okay, come on. First try. So, do we have any doubters? Do we have any doubters in the chat? No doubters. Okay, that's interesting. Nobody wants to lose any points. So people lost their points on the first attempt, right? So now nobody wants to lose the points. Who wants to lose the points? Somebody wants to lose the points. Okay, that's interesting. Prediction not a... Is that like a regional thing? Oh shit. I could see why. Because it might actually violate your local laws about gambling or something like that. That's very interesting actually. Really? Are you guys doubting? You do realize that you're gonna lose your points. Okay, so guys, are you ready to lose your points? Are you ready to lose your points? There you go. I mean, congratulations, you lost your points. So, I mean, that's what you get for, you know, doubting the God Quitter. So... ah! Doubters, yeah, doubters. Anyway, so the second part, oh, part 2, okay. So the game, oh, okay, all right. Part 2. All this drifting around in space makes you wonder about the nature of the universe. Does history really repeat itself? You're curious whether the moons will ever return to the previous state. Determine the number of steps that must occur before all of the moon's positions and velocity exactly match the previous point in time. For example, the first example above takes 2070 steps, they exactly match the previous point in time. It eventually turns to the initial state. Of course, the universe might last for a very long time before repeating. Here's the copy of the second example from above. This set of initial positions takes steps before it repeats. Okay. That is very interesting. Oh, we have a raid from Togglebeat. Thank you for the raid, and hello raiders. Welcome, welcome, welcome. We're programming in Haskell. You know, a superior version of Rust. So yeah, that's what we're programming. So if you take Rust and extrapolate it to extreme, making this superior language, this is what you get. So welcome, welcome everyone. So the thing is, right, so what I'm thinking is that probably the velocity doesn't change for quite some time, right? So the velocity probably doesn't change for quite some time, or I mean, the direction of velocity doesn't change for quite some time. So essentially what we can try to do is, how to put it? Like, given two moons, we can tell for how long it's gonna move in that particular direction. Right, so, and basically, like, step, not by a single step, but by several steps simultaneously, or something like that. So this is my first attempt, like, first approximation. How many steps does it take to reach the first state that exactly matches the previous state? This one is interesting, okay, this one is, like, way more difficult, especially in Haskell. Thank you. I hope you had a good stream as well. Have a nice day. Have a nice rest of the day. The rest of the day. I don't speak English, I'm sorry. Have you checked out the readers? Yes, I have. Determine the number of steps and occur before. So we're definitely not gonna. But we can try. So what's fun is that it also updates the position. So we can step by multiple steps as well. Because it's such a dynamic system, all of the moons are related to each other, right? They're all related to each other, so it's kind of like you have to dig into the specifics of how the system behaves to understand what you can exploit. But what can we exploit there? Find a more efficient way to simulate the universe. Okay, let's try to do like a very dumb way of simulating everything, right? So essentially, we may want to keep track of what systems we have already visited, right? So it could be something like step. So I want to try the dumb way and see. I want to try the dumb way and see if the sample actually performs this amount of steps, right? If it performs this amount of steps.